In today's lecture, we will be talking about the last topic we still have to cover, and that's liquid level sensors. So I'm sure you will see many similar principles that we've already used for different other sensors in the past. So let's take a look first on what possibilities do we actually have if we want to measure liquid level. Now we will see basically two groups of liquid level sensors. The first group will provide us a continuous measurement. So it will be able to give us directly the distance between the sensor and the liquid level. So we will see, for example, that the liquid level in our tank is 5 meters. If it will change to 4 meters, we will see this also with this kind of sensor. The second group will be called point level detection, and this group of sensors is able to give us only the signal if the liquid level is above or below some certain limit. So if you compare those two principles, the output signal from the point level sensor will be a logic 1 or logic 0, yes or no, the signal is there, the signal is not there, and we will not get the continuous info about the distance. We will see that in many cases this is not a problem, because in many cases we just want to know if our tank is full or if our tank is empty, or if we have reached some given level. So we will be able to use those sensors in many applications, and we'll see that if you compare, for example, the prices of those sensors, the point level sensors are a lot cheaper than continuous measurements. If you compare this with position sensors, we will see similarities. When we discussed position sensors, we also had one group of continuous sensors, and the other group was called proximity sensors. It was the same principle, but here in liquid level sensors it's called point level detectors. We will see that also some liquid level sensors will be able to provide us additional info about the properties of the liquid. For example, it will be able to measure density or measure the interface between two liquids that we have in the tank. So we'll also see a little bit into how to measure this. On the picture you can see the selection of principles that are useful for every group. And here you have the sensors for liquids, and here you have the sensor for solids. You can see that in many cases the principles are the same. So we can have a capacitive sensor in liquids for point level detection. We can have the same for solids. We can have the same for continuous measurements. And we'll be talking only about the principles that are highlighted in yellow. So we'll be talking only about capacitive sensors. We'll be talking about ultrasonic, and then we'll be talking about radar and so on. But basically only about those sensors. The other sensors are of course used as well, but we'll be talking about only about the selection. So here is an overview where you may find liquid level sensors. So imagine that you have an industrial process. You have tanks with your products or with your ingredients that you are mixing somehow to achieve the product, and you want to measure how much of the product you have in the tank, or what is the density of the liquid, and so on and so on. So here is our tank, and around it are placed many sensors that can be used for liquid level detection. We can have sensors that measure only in one point, those point level detectors. So for example, here You can see there's a vibrating fork and thermal sensor. That's one example of this point level detector, and we'll be talking about it later during the lecture. On top here you have the continuous sensors. So for example, you can have an ultrasound, you can have radar, you can have other sensors as well that measure continuously the distance between the sensor and between the liquid level. And here on the left you have a very simple example how you may do it as well. You can imagine that we can have a float that is placed near the tank. It is connected with connecting pipes like this, and the liquid level is the same in the tank and in this tube. So this will be the very first example that we will be talking about. And we can see visually directly what is the liquid level in the tank. So let's take a look first why liquid level measurement could be a problem. So imagine that we have a tank like this, and we have a steady liquid level here. We don't have any high temperatures, and so then in this case it's no problem at all to basically use any kind of liquid level sensor to measure the liquid level in the tank. But as we start mixing, for example, if your process requires mixing, if you are mixing some components, then you need to have a mixer in there. And now suddenly it might be a problem to measure the correct liquid level, because here when we're mixing, we of course don't know what is the liquid level. Is it here, or is it there, or is it there, or is it there? So in fact, in this kind of measurement, we try to estimate what would be the liquid level if the mixer is off. Of course, we could measure the liquid level or the liquid content in another way. If, for example, we place 4 sensors under the tank, we can weight the tank, including the liquid, and then we can simply calculate how much liquid we have inside. So this is also a possibility. Without using liquid level sensor, we may use 4 sensors to do this. Let's see why it can be difficult with regards to other problems that we may encounter in the industrial process. So first of all, some liquids may have bubbles. So here you have a liquid, we have some bubble contents in there, and this might be difficult for some sensors. For example, if we would measure this with an ultrasound from the bottom, then we might have a problem because this would be attenuating the ultrasonic signal. So bubbles may cause you some trouble in liquid level measurements. Then we may add foam. Some liquid may form the foam on top of it, and again this might be a problem for some kind of sensors. Again, for example, if you take an ultrasonic distance sensor, in this case you would place it on top of it like this, then you are relying on the reflection from the liquid, and if there is foam, the ultrasound signal will be attenuated, and therefore it cannot be used when you have foam on top of the liquid. We can then add some vapors, and those vapors can be dangerous. For example, they can be corrosive, so they can damage the sensor. So again, we'll see that it's not possible to use all sensors in this kind of application, because we need to protect the sensor itself from the vapors that might damage it. So we'll see, for example, radar that is suitable for this, because we'll have only the antenna in direct contact with the vapors and with the liquids eventually that is in the tank. Next factor might be sediments. So for example, if our industrial process creates sediments on the bottom, we cannot use a sensor that is placed at the bottom of the tank, and that, for example, will measure hydrostatic pressure, because in this case the sensor will be blocked by the sediments. So again, before we select a suitable sensor for our application, we need to think about all those constraints that we have in the process. We may then add high temperature. For example, we are talking about an industrial process where we have 300 centigrades. So only some sensors will be useful for those high temperatures, or it may be even higher if we are talking about 500 centigrades, for example. We may add high pressure. Again, it may be very difficult to select a suitable sensor for all those conditions. We may add acids, so then it may be corrosive for the materials that we have in the sensor. We may add radioactivity and so on. And it may turn out that if you want to measure the liquid level in all those difficult conditions, then it might not be even possible. So before selecting a suitable sensor, you always need to think about all the conditions. Will I have some vapors? Will I have some foam? Will I have some bubbles? Will I have some interface between the liquids and so on? And based on those conditions, only then you can select a suitable sensor. Of course, the last point might be maintenance. So if you need to maintain the sensor, how often do you need to maintain it? And how long will it last in those very difficult conditions? Let's take a look on solids. Solids, it is a little bit different, because solids will create us even more problems than liquids. If you have a tank or silo with solid, then where is the liquid level? Here typically we don't have only one liquid level. It looks like this. Here it's higher, here it is lower. We may have multiple peaks. So if we place the liquid level sensor in here, then it will measure this peak. But if we will place it here, it will measure this valley. So here we need to think about what will be the range where the liquid level sensor can measure, if we should place it on top or if we should place it in the wall or in the bottom to measure the content. And also here you may have openings. So if those are some larger particles like stone, for example, then here you will have openings, and actually the volume that you have is smaller than actually measured by the liquid level sensor. The last thing, sorry, here I forgot to change it from Czech, so let me just do it very quickly. This is interface. So if we want to measure the interface between two components, we may only use a certain group of sensors. Here is an example. Here you can have a liquid, and here you may have a foam on top of it, and here there might be another liquid. A typical example is, for example, water and oil. You want to separate water and oil, and you want to measure how much of water and oil you have. And we'll see also some sensors are suitable to give you not only the liquid level, which is here, but they will also give you the interface between the two materials. If you were to use a sensor like ultrasonic, for example, then if we don't have the foam on top, it might be possible, but it will give you only the first liquid level, so the liquid level here of the oil, but it will not give you the interface. Okay, let's take a look on the comparison between the different groups of sensors that we will be talking about in terms of difficulty and in terms of, let's say, how suitable they are for different applications. So here on this axis we have the price of the sensor, and here on the same axis we have how difficult it is to measure what we want. So if we are talking something about water that has even high pressure, then it's relatively easy to measure this liquid level. Here on the y-axis we have the pressure where we that we want to operate in. Here we see the groups of the different sensors. So if we want to do it with some mechanical device or capacitive sensor, ultrasound, radar, and so on and so on. Here it gets harder and harder. So for example, if we have mixtures, if we have a mixture of water and acids, if we have slurries, if we have mixtures of water and oil and so on, then only some principles might be used. And here if we want to add interface measurements, if we have agitated tank, it gets more difficult. And if we have very hot or cryogenic liquids, if we have vessels with internal structures, if we have high temperatures and radioactivity, for example, it might be even impossible to measure with the sensors that we have currently available. So we'll be talking about the capacitive sensor. We'll be talking about the ultrasound sensor, and then we'll see the radar sensor. Those are basically the groups that we will be talking about. We will not be talking about the laser level and nuclear level. We'll be talking a little bit about the pressure sensor, but not in this case like differential pressure, but we'll be talking about hydrostatic pressure sensor as well. So we'll cover almost all groups that you see here on this picture. Before we start, let's just see why do we need to measure liquid level precisely. It's related to the error that you can have in the measurements. Imagine that we have a large tank. Let's say a diameter will be 20 meters. You want to store some product, and you want to know exactly how much of the product you have in the tank so that you can sell it. So we are basically looking for the liquid level, and we want to know what is the volume of our product. So if we calculate the surface here and multiply it by the liquid level, we'll get the volume. And if we measure the distance, the liquid level in the tank with an error of 10 millimeters, which is very small compared to the 20 meters, then we will have a volume error about 3 cubic meters, which might be very expensive material. So we really need to measure the liquid level very accurately. So let's take a look first on the larger group of continuous sensors, and we'll leave the point level sensors at the very end of the lecture. So the first principle I will show you is the hydrostatic level meter. So it is nothing else than a pressure gauge, and this pressure gauge measures the pressure at the bottom of the tank. So you can virtually take any kind of pressure sensor, you can make a hole in the bottom of the tank, or you can place the sensor directly in the tank on the bottom, and here you measure the hydrostatic pressure. So on the left here we see the example how this is done in an open tank. Here this is the pressure sensor. Here I have drawn it as an example of the well type gauge, but it might be anything else. It might be a diaphragm gauge, it might be whatever you imagine will measure pressure. So we're basically looking for the hydrostatic pressure. So we're looking to measure the hydrostatic pressure on the bottom here at the tap. And using this equation, we can calculate what is the liquid level height here. That's what we are looking for. So for this, we need to measure the density, or we need to know the density. We typically have a temperature sensor in there, so we can calculate what is the density of our liquid. And we simply place the pressure sensor on the bottom of the tank. Now obviously this will not work properly if you have sediments in the liquid. So if your liquid will create sediments at the bottom or at the walls, now this is not a good idea to use this kind of sensor. So this kind of sensor can be used if you have foam, but it cannot be used if you have sediments in the tank. What to do if you have a pressurized tank? In a pressurized tank, the arrangement is very similar. We want to measure the liquid level height, so we need to measure the hydrostatic pressure. But in this case, our reference pressure is not the barometric pressure, as it was the case here. Here we measured the pressure difference between the tank bottom and the barometric pressure of the air. But here we need to measure the difference of pressure between the bottom and above of the tank. So here we need to have a second tab for pressure above the liquid level on the very top of the tank, and this is the pressure gauge. Here it is shown as a U-tube manometer, but again it can be any kind of pressure sensor for pressure difference. Here we basically do not need to have a sensor for pressure difference. It can be absolute pressure, but here we need to have a sensor for pressure difference. So there will be one tab here at the bottom and one tab for the pressure on the top. I recommend you to take a look on this video where they show different arrangements of the sensor, and they explain a little bit more how this is done in industrial applications. Here are few examples of such sensors. Here you can see this is but basically all are deformation type pressure gauges. So although it is called liquid level meter, it is nothing else than a pressure sensor. So here you can see the tab that we connect with the pipe to where we want to measure the pressure, and inside there will be a diaphragm that will change its shape, and we will see the signal on the output. So the output might be some current signal, might be some voltage signal, and so on. We can see a little bit inside here what's actually in this kind of sensor. Again, this is a pressure sensor, so we connect this pipe wherever we want. Here we see that this rod, and this is the diaphragm that we have here. So this diaphragm will change the shape when you apply the pressure. The motion is transferred through this rod into the sensor, and this sensor, in this case, it's an LVDT. So it's a position sensor, and when this rod is moving up and down, we will sense this motion, and this gets transferred to the signal. By judging on this description, this terminal box, this looks like it's a liquid level switch. So point level measurements, because here we have normally closed and normally open and common contact. So it looks like this is a binary output. So it will be used, for example, if you want to fill the tank and you want to stop the pump when the tank is already full. So this will get detected by the sensor, and it will turn off the pump. Here are a few other examples. Those sensors are directly placed in the tank. The ones here on the left and this one on the right. Now the one in the middle, this is a diaphragm sensor. It's again a pressure sensor, so the diaphragm is around here. It can be stainless steel, or it can be ceramics, for example. And you mount this with this thread into your tank, into the wall, or on the bottom of the tank, and you measure the pressure. Now here this has the electronic circuits that produce the output signal, current signal or digital bus, And the sensors here on the left and on the right, you can see that this is the probe, and this is what you submerged in the tank. So here, this is a long cable that you see here, like older different lengths. And this probe sits at the bottom of the tank, or at a given height above the bottom. And there is a diaphragm that measures the hydrostatic pressure. With those openings that we see here and here, the liquid may actually enter to the diaphragm. And when the diaphragm will send us the signal, it gets transferred through this cable into this electronic unit. So in this unit we have an amplifier, we may have a display like this. So this unit then is mounted above the tank, so it's not in contact with the liquid, and the only part that is in contact with the liquid is here. So this is typically made from stainless steel. It may have some plastic parts here. This is typically plastic part, that protects the diaphragm from mechanical damage caused by larger particles, for example. Now, as I've already told you, this is not a suitable principle for applications where you have sediments. So with sediments, it's not working very well, because the sediments will very soon block the access of the liquid here to the diaphragm, and it will cause a malfunction of your liquid level sensor. But on the other hand, it works well with foam. Foam is on top of your liquid and not on the bottom, so it's suitable for applications where you have foam, for example. A few more examples here so that we see the sensors from a different angle. Again, all those are basically pressure sensors. So in all cases there is a diaphragm. Here we can see the diaphragm over there, here and here. In here the diaphragm is actually hidden, and the liquid enters only through this opening that we have here. You can see different versions, opening from the sides, opening in the axis, and so on. We can see here the same stainless steel cylinder. Those holes allow the liquid to enter, they prevent larger particles to get into the sensor, and then there will be a diaphragm and the sensing electronics. Of course, all this will be made waterproof, so it will work when it's submerged in the liquid. And then we see a long cable, and with this cable it will be connected to the second unit, where we actually will have the display, or will have some transmitter for the current signal that we need to connect to a controller system, for example. So what can we expect? Well, this works fairly well up to relatively high temperatures. If you place the sensor in the tank, and if the electronic circuit, of course, is outside of it, then it may work up to temperatures of around 400 centigrades. And the pressures that are typically given by manufacturers is around 400 bars. So very large pressures. It is unaffected by foam that you have on the surface, but on the other hand, it is affected by the sediments that you have in the tank as well. Okay, so now let's leave this pressure principle, and let's see something else. And this something else will be, on the other hand, very suitable for applications where we have sediments. It is called a bubbler. Also, it's called a pneumatic liquid level meter. And the advantage of this liquid level measurement technique is that the only part that is in direct contact with the liquid is a tube and nothing else. So there is no electronics inside. It can be used for higher temperatures, it can be used for aggressive liquids, and so on. So let's see how this works. We will again use the hydrostatic pressure, but in this case we want to overcome the hydrostatic pressure of the liquid with the pressure of some compressed gas. So we need a source of compressed gas. We are blowing this compressed gas into the liquid through a tube, and we are creating a bubble. Here we can see the bubbles that are escaping. Now obviously this requires an open tank. It is not very suitable for a pressurized tank, because then here your bubbles, you would need to remove them somehow. It's possible to do it, but it's more difficult to create. But the only part of the assembly that is in direct contact is this tube. So this tube can be made from material that is resistant to the properties of the liquid, so to the acids or to some other stuff that may damage all those materials. It may be ceramics, it may be stainless steel, and so on. This is working like if you take a straw and you try to blow the air into your glass. And you can try it yourself. If you submerge this deeper into the liquid, then it will get harder to blow the air and to create the bubbles. So we'll need more pressure. And that's basically what is measured with this pressure sensor. So we measure what pressure do we actually need to create the bubbles, and we do this for a given flow rate. So the way this works is that you are trying to achieve a constant flow rate here. This is a flow sensor plus a flow controller, so that here the flow of this compressed gas is constant. And then you can find out that the pressure that you actually measure is a function of the flow, but this is a constant value, but it is also a function of the liquid level here. So if the liquid level is higher, then we need more pressure to create the constant flow. So typically the steady state response of this kind of sensor looks like this. Here we have the liquid level, and here we have the pressure that we want to measure, and it's given by this formula. So it will be a linear response, but then we have the pressure that is given by the flow rate here. So it's looking like this, a linear response. This is for some flow rate, so let's say it will be for Q1. And if we increase the flow that we have in the sensor, it looks like this. It is linear, it is parallel to that, but here we have a larger flow, so we have a larger pressure that we actually measure. So this will be Q2, and Q2 in this case it's larger than Q1. But if we have a constant flow, then we have a nice linear response given only by this formula. So if we want to use this, we need to know only the density of the liquid. So we need to measure temperature, and then we can calculate the liquid level simply by using the signal from this pressure sensor. So this is a very popular approach, because the only part that is in contact with the liquid is this tube, and this tube may be very well resistant to the acids that we have in the process. It works also when you have sediments in the tank. So if there will be some sediments here accumulating in there, the pressure will blow out the sediments from the tube, so it will not be blocked. This can run continuously, so you have no problems in blocking of this pipe. On the other hand, it may be a costly approach, because you need to have the source of compressed gas that is producing the gas at all times if you want to measure the liquid level continuously. This is how it may look like. So this is an assembly where we see all what is required to create this kind of sensor. What we don't see here is the tube itself. This is the controller for regulating the flow. So here we have the supply of compressed air. Now this is a controller where we may set what flow rate we actually want in there. And here this is the pressure gauge. So this pressure gauge will give us the info about the liquid level, and from here we will be having a connection, a simple pipe that will go into the tank, and we'll be able to remove it, we'll be able to maintain it, and so on. So the only part in contact with the liquid is the tube itself, and all this is for, of course, outside. So this can be used very successfully in applications where you have corrosive liquids, where you have sediments. On the other hand, it's not very suitable for applications where you cannot blow this gas into the tank. For example, let's say this would be a tank with beer, and you want to measure how much beer you have in the tank, and by blowing the air you would destroy the product. So the customer would not be very happy about this. So again, it's not suitable for all applications, as all sensors. Okay, let's take a look on the third principle, and this will be a larger group of capacitive liquid level sensors, and we'll see a different arrangement for different kinds of liquids. Some will be for conductive liquids, and some will be for non-conductive liquids. Now in all cases we want to measure the capacity, and this is the basic formula that you know from physics, that is telling us that the capacity of a capacitor is given by the properties of the dielectric material. This is shown here as epsilon 0 and epsilon r. So epsilon 0 is the permittivity of vacuum, epsilon r is the permittivity, the relative permittivity of the material. Now this formula is for electrodes where you have planes, so it's for planar electrodes. So if we have an area A and distance d between the electrodes, so we can see that if we can change basically all three, but in capacitive liquid level sensing, what we are doing typically is that we're changing just the epsilon r. So we're basically changing the material that we have between the electrodes. Here you have two examples. Let's start first with this one. In this case, now those electrodes are cylinders. So here in the middle we have one cylinder, that's one electrode, and here the second electrode is the tank itself. Now the formula will be a little bit different, but still the same logic will apply. The capacity that we will calculate will depend on the material. Here we have the liquid, which has some epsilon r1. Here we have a gas, air, which is epsilon r2. So this is what is changing. It will be also dependent on the distance between the electrodes. So the distance between this electrode and the tank will be also important, but this is a constant in our setup. And it will also depend on the area of the electrode. So we may calculate also the area of this cylinder and of this electrode and get the capacity. So we'll see a little bit later what is the formula for this. The arrangement that you see here on the left is for a non-conductive liquid. So here this liquid needs to be non-conductive electrically. Otherwise it would short out the two electrodes together. So here this electrode would be directly connected to the tank itself. In this arrangement we actually can get three capacities. The one capacity, C1, is given by the contribution of this part, of this capacitor here. In there we have this height, so this will give us the area. We have this distance between the electrodes, and we have this material, so this will be C1. Then we have this capacity. This is air, and again here we have this distance, which gives us the area. We have this distance between the electrodes, and we have this material. And then we have the third capacity that I will call C0, and this is the capacity of the cables, of the connection, of the whole assembly. And this is typically a constant value. So as our liquid level is changing, if it's increasing, let's say, then we'll get a larger value of C1, we'll get a smaller value of C2, and we'll get constant value of C0. We'll see the equation in a minute. Now, if you have a conductive liquid, you need to electrically insulate the electrodes from the liquid, and you need to insulate at least one of the electrodes. So typically it's done in a way that the middle electrode is insulated, and here we see the insulation, and this is the liquid level, but this liquid now is conductive. Since this is insulated, it will not be in electrical contact with the middle electrode. So here again we have the same arrangement. We are looking for C1, which is given by the changes of liquid level. C2, as H is increasing, C2 is decreasing, and C0 is the constant capacity of the cables, of the connectors, and so on. So basically what we are looking for is the dependence of the capacity of this cylindrical capacitor on the height here. And now this formula that you see on screen, this is just to show you how this is actually derived. But what is important here is this final result. In this result we see that it has the same or similar structure as the previous equation. Now the previous equation was C is equal to epsilon times A over distance. Now in case of a cylindrical capacitor, we have the area given by the height here. That's what we want to measure. So this A now corresponds to this H, and since this is a cylinder, now the distance between the electrode and the cylinder is calculated like this with the natural logarithm. Here you can see the derivation why this is so. So we can see also that this is the material, this is the height, this is the area, and this is the distance between the electrodes. So it's a very similar structure that we have over there. So as we are increasing the height, here we are increasing the capacity, as we are basically decreasing the height here of the gas column, of the air column. Then now this means that we are decreasing the capacity of C2, and therefore the final equation that we will obtain will be very simple. It will be constant times the height that we have over there. So it is given like this: C0, that's the capacity of the connectors, that's constant, plus C1 plus C2. And here we have simply substituted into the equation for the cylindrical capacitor. So this is the liquid level that we want to measure, and this is the column of the air that is above the liquid level. Here you can see that this is H, and here we have the total height of the tank minus the liquid level that we actually measure. Now if we look on this equation, then epsilon 0 is constant, epsilon r and epsilon 2 is constant if we don't change the temperature. The both these are constant as well, because this is not changing the geometry, and hence all this is a constant number, so let's call that k. And here this is constant as well. So now if we simplify this equation, we'll get this result. It's some constant times some other constant times h. So this is nothing else than the equation of the line. So if here you have the liquid level height and here you have a constant capacity, then it will look like this, where this will be the constant k1 and the slope that we have here. So let's draw it like this. So the slope here basically they will be called k2. So this is a nice linear equation. Now let's take a look on how this will be different if we have the planar electrodes. So if it's a plate like this, and we'll see that basically it's exactly the same thing. We have capacity C1. Here this is the capacity given by the liquid level. C2 is the capacity given by the air column here, and C0 is again the constant capacity of the cables and of the connectors and so on. Again, if we sum all those capacities, we'll be able to obtain this equation. Here you see the height and the B and D. This is the D is the distance between the electrodes now, and B is the width of the electrode, and H is the height, the total height of the electrode, so the total height of the tank. But we see that again it has exactly the same structure, so all this is constant and we are looking for H. So we will see that it again will give us the same formula, some constant, let's call it K1 plus K2 times H that we want to measure. So the result is the same, although here we have a different setup. Note on this picture that this picture is shown for a non-conductive liquid, so there is no insulation on neither of the electrodes. So this arrangement would work only for a non-conductive liquid. So for example, if you measure the oil, then it would work. It will probably not work with water. Distilled water, it will work fine, but normal tap water will not work because it's slightly conductive. So the recommendation is that you should always insulate at least one electrode, even if you at least if you don't know what are the electrical properties of your liquid. Now let's take a look on some industrial examples. Those are industrial sensors that are used to measure liquid level in a tank or of a car, for example. And those are capacitive based. You can see here that this is the cylinder that I was talking about. Now this is the middle electrode, so now this will be the rod that goes like this, and the second electrode will be this cylinder. So this tube is the second electrode and this is the first electrode, and the liquid will enter into the sensor with those holes. It will fill the sensor, so it will go all the way to the liquid level, and you will evaluate the capacity of it. So this is inside of the tank, and this is outside of the tank. So this is the electronic circuit, or just some terminal box that allows you to connect all this together. So now in this case it looks like it's from brass. In this case it looks like it's from stainless steel. So the materials will vary based on the application where you actually need to use it. Again, here we see the cylindrical arrangement. Here the liquid enters with this hole inside. This cylinder is one electrode and the other electrode will be a rod that is inside of it. And this hole allows the air to escape when you are filling this column in the tube. So This is then mounted on the tank. Here you can see the seal, and this will be the electronic circuit, and then here with this connector we will get the signal to our controller system. A few more examples. Here we see the arrangement where we have actually the two electrodes. So here we have two electrodes. It's not visible if they are insulated or not, probably yes. And again, this is where you mount the sensor in the tank, and here you have the electronic circuit. Here we see inside of the sensor. So here we see the tube, that's the external electrode. Here we see the internal rod, that's the internal electrode. And again, there will be some openings in the bottom to allow the liquid to enter. And here those two holes to escape the gas from inside. And this kind of sensor will use the tank walls as the second electrode. So here this will be the mounting. This is one electrode, and the other electrode will be the tank itself. So it requires that you have a conductive tank made from some stainless steel, from aluminium, or some conductive material. Here we see what's inside. So this is the cylinder that you submerge actually into the liquid, and this is the electronic circuit that basically changes the capacity into some electric signal. So here this looks like it will be a current loop, 4 to 20 milliamperes for example, and this whole circuit will be powered from the current loop, and the current will be proportional to the measured liquid. So it's a relatively simple sensor. It's a continuous sensor that gives you continuous readings of the liquid level. Now obviously you may change the length of the electrodes here based on your application. It may be longer or it may be shorter. So what can you expect? Capacitive sensors are suitable for applications that have aggressive media and heavy buildup. The buildup means that the material sticks on your electrodes, but this can be compensated. On one of the videos I have inserted here in the links, you may actually see how this works and why this is working, but it's suitable also for those applications. It is suitable for aggressive liquids because the only part of the sensor that is in contact with the electrode is the electrode itself. So it may be from stainless steel so that it's corrosion resistant for your material. You can use either the arrangement of with two electrodes or with one electrode, and you may even use the tank or silo wall as one electrode directly. So if you have a stainless steel cylinder, stainless steel wall, you may use this directly as one electrode, so you save on the material for the sensor. It is suitable for about the same temperatures like the previous sensor, the pressure gauge, so for about 400 centigrades. Of course it depends on the materials that you have for the electrodes and so on, so it may be a little bit smaller, it may be larger, and it is for about the same pressures. Here in this manufacturer is telling that it was suitable for 100 bars, but you may find larger pressures or smaller pressures. You can see a last example here of this capacitive sensor on the right. The next principle will be ultrasound. This will be we've already seen this principle when we discussed position sensing, so I will cover this only briefly. And again, I recommend you to take a look on this video, on the links, because they are quite interesting, and you may see where this is useful. So let's have a tank like this, and we want to measure the liquid level height in the tank. Now in the case of ultrasonic sensor, this is nothing else than an ultrasonic distance sensor. So we place the sensor above the liquid level, like that. And we are producing an ultrasonic signal. So now this is a transmitter and this is a receiver. We send the ultrasonic signal, like that. Now on this interface between the air and the liquid, it will be reflected. And here we time when we receive the echo at the receiver. Now obviously the delay between the transmission and reception will be a function of the distance. So we measure some time t, and if we know the speed of sound in this gas, then we may calculate what is the distance between the sensor and the liquid level. Now we're looking for h for the liquid level, not for distance. But if we know the height of the tank, we can simply subtract the measured distance from the tank height. So this is nothing else than a distance sensor. Here are few examples. It's mounted above the liquid level. You can see here this mark. This gives you the reference where does the sensor start the measurements. So this is, let's say, distance 0, and it's typically sealed in hermetically sealed containers so that it does not get damaged with water and with some dirt, for example. And the ultrasound is then projected in a. It looks like this. The projection. This is the cone, like that. And in the data sheet, you typically find what is the distance or what is the angle of the cone. It's typically very narrow. It's something like 1-2 degrees approximately. So it can be used also in very narrow tanks. What can you expect? Now this principle is unaffected by product properties, because we are not looking for some density changes or moisture and so on. We are looking just for the interface. So the interface is what we measure. On the other hand, if the interface is with a foam, for example, then this will not work properly, because the foam will attenuate the ultrasonic signal and hence will not get the reflection that we are expecting. So the ultrasound meter is not suitable for foam on your liquid. So if you again measure the liquid level in the tank with beer, then it's not a good idea to use ultrasound, because the ultrasound will be attenuated by the foam that you have on top. It is suitable for lower temperatures than the previous sensors, so typically about 150 centigrades or smaller. The part that is in direct contact with the tank inside is this part here. Now this is the ultrasonic transducer, so it's a transmitter and receiver at the same time. Here we connect that with this thread, so you are also limited typically in pressure. So in terms of temperature and pressure, it is less performant than the other sensors, but it may work with applications where you have sediments and so on. So it typically looks like this. This is the sensor itself, and this is the transmitter. You may have a display that locally displays and allows you to configure the properties of the sensor, for example the range or the type of the output signal and so on. Okay, so that's ultrasound. Very similar will be radar, so we'll not get again too much deep in this kind of sensor, and plus we've already seen it when we discussed position sensing. Now the difference between the ultrasound and radar is that ultrasound works with sound waves, but radar works with electromagnetic waves. So there is a huge difference in the speed of propagation here. Now in ultrasound, this was the speed of sound, and we were looking for the reflection. Now in the radar, this is speed of light. You can calculate the distance using this formula. C0 is speed of light. Time is the time difference between the transmission and reception of the signal. And mu r is the permeability, so it's a property of magnetic circuit. And epsilon r is permittivity, so that's those are two constants given by the material. But if we know this constants, then we can calculate what is the distance between the transmitter and receiver. So it basically works in exactly the same way. We transmit the signal, we wait for the reception. But the huge difference is here in this time. Now in ultrasound, this time may be something in the order of milliseconds, for example. But for the radar, this time will be in the order of picoseconds typically. So many orders of magnitude smaller. So it may be difficult to measure this small time, although it's not impossible. For this reason, many radar liquid level meters, they use something that's called frequency modulated continuous wave, FMCW. The way this works is that you have a transmitter and receiver as well, but now you're not sending the pulse of the signal here, so you're not sending a beep and waiting for the beep to be received, but you're sending a continuous signal. So here this transmitter now is sending a continuous wave. We are changing slightly the frequency as we are transmitting it. So here we are sending a signal with variable frequency. Now this gets reflected from the object, and this object might be an object like a car, for example, if it's a distance level, this distance sensor, or it might be the liquid level itself. And we receive the signal here. This is the reflection that we receive. The received signal will be also a continuous signal with a variable frequency, but there will be a frequency difference. Here we are comparing the frequency that we are sending right now with the frequency that we are receiving right now, and the frequency difference will be proportional to the distance between the sensor and between the object. And now the advantage of this is that we are not looking for a very short time difference, but we are looking for a frequency difference, which is relatively easy to get. So then this circuit that is called phase detector is comparing the frequencies here and here, and the output signal is proportional to the distance. So now this is how it looks like. This is the antenna, and the antenna is in direct contact with the tank. It's inside of the tank. It can be made from stainless steel, so you can see this is like a horn antenna. It's a cylinder with that's made from stainless steel. We mount this with this flange into the tank, and that's it. And this electronic unit then sits outside. So this is the transmitter and receiver, and here this is just the antenna itself. So typically this works with very high frequencies. Now the frequencies that are used in industrial systems for this kind of radar measurements are typically 6 gigahertz or 26 gigahertz. Today, in the last say year or two, a new band was added that is around 80 gigahertz. So it allows you to work with higher frequencies with higher accuracy. It can work with high temperatures because the only part in contact with the other vapors and liquids is the antenna itself. And it can work with relatively high pressures. So again, you need to seal this antenna, and that's basically it. It is suitable for applications where you have vapors and you have dust, and also for applications where you have variable temperature, for example, because although the properties of the gas above the liquid will change with temperature, the dependence is not very large, so it's suitable for those kinds of applications. On the other hand, this radar liquid level meter, it's quite complicated, and therefore it's quite expensive. Now if you compare, for example, the capacitive level meter, that might be something like, let's say, $100, $200 US. This radar liquid level meter would be something like maybe $10,000 US. So there is a really huge difference in price of the different sensors, and you need to adjust the sensor selection based on what you really need in your application. Now we tried to get one radar liquid level sensor in the school labs. We currently don't have any, but it's about maybe $15,000. Okay, so that's all for continuous sensors, and now let's talk at the end about point level measurements. So all those sensors will not give you a continuous reading. They will give you only yes or no. So it's kind of like a proximity position sensor. We'll see that again, some of the principles will be very similar to the continuous reading, but we'll just have a different electronic circuit that evaluates the signal. I will show you only, I think, 2-3 examples. What you see here is based on electrical conductivity. So now this works only for conductive liquids. So if you will measure oil, then it will not work. But if you measure tap water, it will work. If you measure distilled water, it will not work either. So we are looking for a conductive liquid that is connecting two electrodes together. So here on the left you can see an example how we could use it to measure continuously. So this would be continuous reading. So it is somewhere between the point level and continuous group. It's actually in both. Here we have two electrodes. We are looking for the current that is flowing between the electrodes, and the current is flowing into the liquid here. This is my tank, and here I'm looking to measure the H, that is the liquid level. Now if H is getting bigger, the conductivity is changing, and conductivity is the same, but the amount of current is changing because we have a larger area here, and therefore the current will be proportional to H. So that I will measure current, and now current will be proportional to the liquid level that I want to measure. So I can calibrate this and I can get continuous reading. I can use this also just as a limit switch. So if I want to see if the tank is full, I will install two electrodes like this, and those two electrodes will be used if I want to detect when the tank is empty. So we can see here that now the current is flowing through those two electrodes because it's above them. But now I'm not looking for the current value, but I'm just looking if the current is above a given threshold, so above 0, for example. And here this is now connecting the two electrodes together, and I know now it's above the minimal level, but I don't know where exactly it is. Is it here, or is it there, or is it there? And I'm looking just for the upper limit. So here, when the liquid will rise above this limit, it will connect those two electrodes together, current will start to flow, and now I know that the tank is full. So here, in this case, this output signal will again not be a continuous current, like a continuous signal, but I will see only 0 when it's below and 1 when it is above. So I will not have a continuous reading of the liquid level. I will have only info from this upper limit switch and from this lower limit switch. What can you expect? Now this needs obviously a conductive liquid. So if the conductivity is above some minimal level, it will work. It will work for temperatures of approximately 150 centigrades, pressures about 25 bar. This again, those numbers are from manufacturer data sheet, so I've selected one manufacturer and those are the numbers. Other may be providing different temperatures and pressures. That's clear. And here we can see an example. So here we see the 3 electrodes. So this will be able to give us 2 liquid levels. So this will be the reference electrode, and then here and here we'll have the 2 electrodes that are able to measure the liquid level. So if my liquid level is above this, then it will connect those 2 electrodes together. If it's above that, it will connect all the electrodes together, and I can get a reading from there. Okay, a few more examples. It may look like this, so different numbers of electrodes. You can see here they have 4 electrodes, here they have 4 electrodes as well. Here in this case the electrodes are covered with this ceramic pipe. So again the liquid enters through this hole. Now there will be probably 2 electrodes like this inside that are mechanically protected, and now they will be shorted basically by the liquid that enters in there. So this is like a combination of the continuous reading and point level detection. The last principle that I will show you is this is only a point level sensor, and it is called a vibrating fork. Now this is suitable for liquids and solids. Now, all the previous examples were suitable for liquids only, except the capacitive sensing on, well, maybe the ultrasound and radar. But this is a sensor for point level only. Now the way it works is that we are looking for vibrations of a mechanical assembly that looks like a fork. So it has this shape like a fork, and we are imposing some vibrations. So we have a piezoelectric exciter that makes this vibrate, and then we have a detector, again a piezoelectric crystal that detects the vibrations. And again, I recommend you to take a look on this video so that you can have an idea. They have a very nice animation there. Now in this setup, in this example, we see 2 vibrating forks. One is in the liquid and one is above the liquid. Now the way this works is shown here. Here this is the vibrating fork. Now this is vibrating like that. This is the liquid that we have, and this is the circuit that makes it vibrate. So this is actually a resonance circuit created by the piezoelectric exciter, by the fork and other electronics as well. So now this vibrates back and forth. The frequency and amplitude of the vibrations will be different if the fork is submerged into the liquid or if it's not. So basically we are looking for changes of amplitude and eventually frequency of the vibrations. So as soon as you submerge it into liquid, you will get a different amplitude and different frequency. So this is then detected with an electronic unit, and if the change is above a given threshold, then it will give you a signal. So the signal here would be, for example, 1, liquid level is above so the fork, and here the signal will be 0, liquid level is somewhere below the fork. But again, we don't know where exactly it is. So here this sensor would be used to detect minimal level, and here this would be used to detect maximal level. So for example, if you want to fill the tank, now you will turn on the pump until this will disconnect the pump, and the tank is then full. And then you're pumping out the liquid. Here this checks if the tank is already empty, and you may turn off the pump so that you don't pump the air from the tank. Here are few examples. Here is the vibrating fork itself, so it's typically stainless steel. Now this vibrates like this, so this vibrates like that, and this vibrates like that, very small vibrations. Now typically in this part there is a stack of piezoelectric crystals that you have the piezoelectric crystals stacked like this on top of it, and now the vibrating fork is in there, and here there is a diaphragm, and you're deforming the diaphragm, and the deformation is created by the piezoelectric crystals, and now this makes the vibrations, and you measure the vibrations, and now this electronic circuit evaluates the amplitude and gives you a signal. You can see that they look the same basically from all manufacturers. Here they have this vibrating part in there, and the difference is in the sensitivity, of course, in the protection and so on, but the principle is the same. Again, I recommend you to take a look on the videos in the links, because they are quite interesting. You can see inside of the sensor how this is actually arranged with this stack, and how does it work for liquids and for solids. A few more examples. It can be mounted directly in the tank, so you can see here different versions. This is the fork itself, this is where you assemble it, this is the electronic unit. It may be also hanging from the cable, so again, this is in the tank, you just submerge it where you need it on this cable, and this is then sitting somewhere on the top where it will not be harmed by the mechanical damage or by corrosion that you have in the tank. So now this is quite often used in water treatment industry. If you want to clean water, for example, you need to measure the water level that you have in the tank, so this is quite useful. It's a very robust sensor. Here this is the only part that is in contact with the liquid itself. Obviously this is hermetically sealed. At the end, let us see what we can expect. So now this is only a point level switch, so no continuous reading. It can be used when you have bubbles and foam. That's not a problem, because you are looking for the liquid level. It can be used also to detect solids that are underwater. So if you have a tank, for example, like this, here is the water level and here are the sediments, then you may have actually multiple sensors of this kind. You may have one sensor in here that detects the liquid level, the water level, and you may have a second sensor in there on the bottom that detects the sediment level. And when the sediment level is above some threshold, you may schedule maintenance, you may empty the tank, you may remove the sediments, and you may continue in the process. So now this works also underwater. It is possible to use this for all pumpable liquids up to approximately this viscosity, and it is not impaired by turbulence, foam or bubble that you have in your process. Okay, now at the end, here are two videos that compare the two principles, well, several sensor principles together. So I recommend you to take a look on that. And that's basically all for today.